Hi everyone, good evening. Welcome to this webinar on linear regression algorithm for data science learners from InsideAIML. Today we're going to discuss about the most fundamental algorithms, that is practically a building block for most of the algorithms that have a way of reducing error and fitting lines to different kinds of patterns that we observe across channels and domains. Right? Linear regression is one of the very early algorithms that made the foundation of predicting a value based on a certain set of current known existing values. For example, if you want to predict the sales of a company, you might need variables such as current market value, GDP, marketing spends, let's say mobility. What about other competitor brands that are spending? What are their growth numbers or sales? And using all of these variables, you can help predict your own sales, right? So a linear regression algorithm that we are going to discuss today in a lot of depth is basically consisting of regression, right? Regression is a very large term. It covers a lot of secondary models and algorithms within it. But what is primarily regression? Primarily, regression consists of one and one thing only: the ability to predict scalar values, right, in a continuous range. For example, if I predict fraud, then there are only two possible values. Either it's a fraud or there is no fraud, right? But when I want to predict the sales, the revenue, let's say the heart rate, the BMI, the price of a house, all of these things, they lie in a large continuous range. There is no discrete output. In a technical statement, it's called a regression has a continuous space output. The opposite of that is something known as a classification model, where classification is dependent on a discrete output space. There are known discrete output possibilities. For example, fraud, not fraud. What was the review for the movie? Good, better, best, or let's say bad, neutral, good, right? It can be any of these three, but it can only be these three. There is no continuity. It's a discrete space, selective number of possible outputs. Okay. Now, before getting further into regression, we will also talk about the fundamental ideas behind modeling or building algorithms. For example, what are independent variables? What are dependent variables? What is the line of regression? What do you mean by fit? How do we view or visualize data points, etc., etc. We'll also be looking at a lot of regression use cases. By the way, I'm looking at the chat so that if anyone has any questions, I can answer them. So if you have any questions, just post it on the live chat on YouTube. We'll also be talking about regression use cases. I mean, how is it used in the real estate industry, in the banking and finance industry, in the healthcare industry, in the supply chain industry, where and how we can use it. The different types of regressions, we'll first classify them into simple and multivariate, then linear and non-linear, and we'll just combine them together. Then we'll talk about the fundamental method to fit a linear regression model, which is called the least squares method. And then we'll also do a quick implementation of the same in Python. We'll go live on a Jupyter lab and we'll code it out by getting dataset online and show the linear regression model. Okay. Moving forward. So what is regression? In a very simple terms, it is a statistical algorithm to quantify the strength and character of relationship between two or more variables. Let us simplify each and every aspect of this. First of all, it is a statistical algorithm. It is not a mental model. It is mathematically proved, mathematically derived. Okay. It is not something that is random. It is a statistical algorithm. It quantifies. Quantify means what? It tells you a number. It gives you a number. Okay. For example, if I ask you a question, how much time will it take? You can answer it will take some time. Then you have not given me a quantity that I can associate with. Some time for you can be half an hour. Some time for me can be an hour. Some time for someone else can be 10 seconds, right? So we are quantifying the value. That means I will take 5 minutes. So now you have a 5 minutes value, which is generalized. So 5 minutes across the world is the same. Okay. That is the meaning of quantifying. The strength and character. So there are two aspects of it. When we consider two things and how they impact each other, for example, how much you invest in marketing and how much sales you get. These are two variables. Now, marketing impacts sales. Okay. Sales does not impact marketing. Very, very important concept. There is something called as a independent variable and something called as a dependent variable. What is an independent variable? A variable that we can manipulate or influence. How much marketing do I have to do is in my control. What amount, which channels, which marketing campaigns do I take is in my control. So it is an independently acting variable. But from the marketing I do, how much sales I get, that is not under my control. That has a lot of other factors. Sometimes sales depends on weather. If it is raining for the last 10 days, my product might not be sold at all because people are not able to reach the shops, right? So it is not dependent on me. It is dependent on multiple factors, right? Let's say suddenly India's economy, got a little disturbed for any which reason. Let's say the war got announced between Russia and Ukraine. The sales of a lot of companies dropped down. Was that something that we could control? No. So sales, which is the output, is a dependent variable. An independent variable is marketing, something where I invest. How many employees do I hire? That depends on me. How much raw material do I buy? That depends on me. But after doing all of that, how much sales I get is not dependent on me. So that is why the concept of independent variables and dependent variables. So regression is a statistical algorithm that helps us find the relationship between two variables, dependent variable and independent variable. How do we understand the relationship? By strength and character. What is the strength? How much does it impact? What is the power of impact? Suppose if I invest 1 rupee in marketing and I get 2 rupees sales, that means it is a double impact, double strength. 1 rupee invested gives me 2 times of sales. But let's say if I invest in my employee, every single employee I hire, my sales increases by 5-fold, right? Because one employee can contribute to making more quality product, more quantity of the product. And so let's say my sales goes up 5-fold. So what is the strength? The strength is how much does investment in any independent variable or change in any independent variable affect the dependent variable, the output variable. And character, which direction does it append? Which direction does it affect it? Does it do a positive impact or does it do a negative impact? Right? Suppose adding more employees or doing more marketing will give a positive impact on my sales in the usual case, not considering any particular exceptions. But let's say I did some negative marketing or my competitor did some marketing for themselves. Okay, my competitor did a marketing campaign for their own company. What happens? There is a negative impact on my sales. So a regression model gives you the strength and character of relationship between two or more variables. Okay. It's very important to understand to first judge if something is a regression problem or not. Okay. A lot of times you need to first decide the problem that I'm solving. Is it a regression problem or not? Okay. Let's look at this with some examples online. Regression versus classification. Okay. Look at this example. When I want to predict a value, a number, that is a regression. When I want to predict a class, a category, okay, a distinguished category, that is a classification problem. Okay. A simple example could be doing some medical analysis. Let's say I get the medical image of the blood sample of a patient. Using that, I can predict if the patient has sugar or not, if the patient has a good immunity system or not, I can figure out if the person has cancer or not, any terminal disease or not, all of those situations, right? What are these? These are classification problems. I will either say yes or I will say no. So my answer is not a number. My answer is a category. Okay. On the other hand, if I want to predict the price of a house, number of rooms, that is an independent variable, now which is already existing. The area of the plot, the parks nearby, school nearby, all of those things. These are inputs. What is the output? The price of a house. Now the price of a house cannot be good or bad. It has to be a number. So a regression problem is basically where we are wanting to look at a number. Okay. And a classification problem is where we are looking at a class, a category. Dependent and independent variables, I hope we are clear. Coming to data points, the data points can be just 2 columns, 2 random variables, or they can be more than that also. There has to be one dependent variable at least, and one independent variable at least, but there can be multiple dependent elements and multiple independent elements as well, okay, to do a model. Very interesting is the idea behind relationship, okay. Let me show you an example. Okay, let's look at this. Suppose I am hiring for my team. Okay, I work at a large company and I am hiring 10 to 20 people for my team. The more number of people I hire, the higher my employee cost goes, right? Let's consider one employee comes at a constant cost. Okay, constant CTC is what I'm going to offer them. As many number of employees I hire, my cost will increase constantly. Okay, suppose one employee comes at a cost of 5 lakhs. 10 employees will come at a cost of 50 lakhs. 100 will come at a cost of 5 crores. Right? 10 employees, 50 lakhs. 100 employees, 5 crores. So the relationship is linearly increasing. There is a simple math. Y is equal to mx. In our case, m is the cost of one employee. X is the number of employees. And y will be our total cost. So y equals number of employees into cost per employee. So that will be a straight line because it is going to increase by a same ratio. What is the ratio? The cost of one employee. The more I add, the more cost will increase, but the cost will be a straight line, which you can see here, a linear relationship. On the other hand, there is something called as a non-linear relationship. Okay, what is a non-linear relationship? Where upon increasing x, the y does not increase consistently. The y can decrease, the y can increase in any which way. The y will not be a straight line. The curve is not a straight line, right? So that is a non-linear relationship. Non-linear relationships can look in different ways. This is also a non-linear relationship, right? This is also a non-linear relationship. If you can see the semicircle, right? Look at this. Quadratic is also a semicircle. Exponential is a semicircle. Like you guys have all seen Warren Buffett's finance curve, right? Have you guys seen this image? Right? So when he started investing, he had some money, then some more. But suddenly, in the last few years, his net worth has jumped by this. So this is not a straight line increment. This is a non-linear improvement in his wealth, right? So that is why we say it's a non-linear curve, right? And let's say you are earning a salary, right? So every month, your time increases, your total wealth increases, right? It's not a non-linear increase in your wealth. It's a linear increase in your wealth. I hope everybody is clear with that. Just put a yes or no on the chat so I'm clear. If you have any questions, let me know, right? So there are two types of relationships, linear and non-linear relationship. Univariate and multivariate. What do we mean by that? Univariate basically means If there is only one independent variable, then it is a univariate value. One second, let me check the chat. Okay. So univariate means there is only one independent variable. Multivariate means there are more than one independent variables. Okay. So let's say if I want to predict the price of a house based on its square feet area, only based on its square feet area, then it is a univariate regression problem. But if I want to predict the price of a house using the area, number of bathrooms, number of bedrooms, size of the hall, what is number of floors, does it have a swimming pool or not, all of these other factors, then it is a multivariate regression problem. Okay. The relationship is quantified. That means my final equation will always look something like y, which is the dependent variable, is equal to slope, which is basically the relationship, let's say mx, 5 of x, y is equal to 5 multiplied by x. So how much does x impact y? 5 times. Let me give you a mathematical example to prove the logic. Okay, I'm going in a Jupyter notebook so we can write math equation. Y is equal to mx plus c. This is the equation of a linear univariate, by the way, univariate linear regression model. Okay, this is the default equation. Now you have your data. Once you have your data, this equation will be solving for the unknowns. What is the unknown? The value of m, 4.3. Let's say I'm giving an example, 4.3x plus 10. Now observe carefully, m and c are my unknowns. M and C are unknowns, right? My specific data fetches the value of M and C. Okay, so y equals 4.3 times x. Now consider the case where x increases by 1 unit. What is the new y? 4.3 times x plus 1 plus 10. If I solve it, y new is equal to 4.3 into x plus 4.3 plus 10. If I rearrange it, y new is equal to 4.3 times x plus 10 plus 4.3. This 4.3 times x plus 10 is my old y. So I can replace this with y. So my new y is original y, this particular y, plus 4.3, which 4.3 is the quantification of the relationship. So my x impacts y with a positive 4.3 magnitude, right? And that is my slope. Because this 10 value that you see here, this 10 is a constant. Let me give you an understanding of what the constant is. Let's say my current sales is equal to marketing into 1.5 plus employee count into 30 plus let's say another variable, machinery count into 1.6 plus 200. Okay, this 200 is my sales even if everything else is 0. Did everyone understand that? Yes or no? This 200 is my sales even if machinery count is 0, employee count is 0, marketing is 0. Why? Because let's assume this is my default customers. Okay, these are my loyalty customers. Even if I do not do marketing, they will still buy my product. Okay, let's assume for a healthcare company. For a healthcare company, they have 500 units of medicine sold constantly every month. So these are their permanent customers, right? So this additional constant value represents that value, the permanent value that does not change upon any dependent, independent variable, right? Character of relationship. Now in this particular value, you can see I can have a marketing into 1 plus 5 plus, let's say I can have minus 1.2 times into competition marketing. If my competition also does marketing, minus 1.2 times of my sales, right? That is also an idea. So this is 1.2 is the strength of the impact. Minus is the character of the impact. Okay. Coming back. We also must do visual inspection, just like you can see. If you observe that the relationship is not linear, then you should not be fitting a linear model, right? Any questions so far, guys? I'd love to take questions. Okay, so I see no questions yet. I will proceed. Okay, now we've obviously understood that regression is what we are going to predict. When it's going to be a number, then it's a regression problem. Classification is if we are predicting a class, hot or cold, right? So the corresponding models that work for regression and classification also have a difference. When you are looking at a model, the equation predicts a number. So the algorithm behind it is a mathematical model, which is arithmetic, right? It's like a arithmetic model, plus, minus, multiply, divide, etc., etc. When we are doing classification, the background is a probabilistic model. What do we mean by probabilistic model? Where the output is based on a probability. Okay, so in classification models, the output is a probability. So let's say, will it be cold or hot tomorrow? The prediction will be with a probability of 0.7, it will be hot tomorrow. With a probability of 0.3, it will be cold tomorrow. So what is my prediction? My prediction is that it will be hot, but my probability of hot is 0.7. 0.3 is the probability of being cold. So whatever value is greater than probability of 0.5, that is considered to be my output. But even though we are saying hot or cold, we are not absolutely saying hot or cold. We are saying hot with this probability, cold with this probability, right? Moving forward. If you also look at this curve, you can clearly understand dependent variable, which is something that we cannot manipulate. It is basically an output, a result. B naught, which is the intercept or the constant value that I cannot change, it already exists. Then comes beta 1, which is also something we looked at, like M, right? Which is the strength and character of relationship between Y and X, where X is the independent variable which we can change, we can manipulate. And obviously, this equation will never be 100% exact. There will be some random error component, certain things that we have not recorded in the data, that we cannot record in the data. For example, every day, I can never predict with exact accuracy the price of a stock, even if I have the best models in the world. right? There will be some random error component that I can never track, right? For example, mood of a person, right? It depends on a lot of factors. Yes, I can use if he has eaten healthy, what time did he wake up, has he had a good time, good sleep last night. All of those factors affect. But any small message, any social media text can simply turn off the mood of one person. We never know, and that's random. That's not in our control. So that is why there is an additional error term, a random error component, which we don't want to learn. We just know that it exists, right? Now, what are the different regression use cases? Obviously, supply chain, demand and supply forecasting. Let's say I work for a large manufacturing company, right? For a particular season, I know that a lot of requirement for my product is going to come in the market. Let's say you are coming from the paints industry, right? When do people paint their homes and walls? There is obviously this year-long, purchase. There are a lot of people who are just going to get their house painted anytime, right? Whenever they need it. So that is my constant value, constant average sales of paints throughout the year. But there are certain periods when people renovate their houses. Okay. So depending on which part of India you are in, depending on which festivals you celebrate, a lot of people get their houses renovated, new furniture made, new color, new paints before their major festival so that their house is beautiful on that day, right? A lot of Indians do that on Diwali, right? A lot of other religions would be doing it on different festivals, important festivals of theirs, right? Let's say in US and America, US, UK, different places, Christmas is a very important part because before that people decorate their houses. So the paints industry, although is a year-long industry, but it also has some seasonality. So before the upcoming season, the supply chain managers have to plan for the incoming demand, right? And they also have to forecast how much they should supply, when they should supply, so that the prices are balanced. If they supply a lot of material, okay, and the sales does not come, if like let's say I've sent my product to the shop, but there is no customer buying it, then I will have to spend an additional cost in transportation. So they are going to predict the demand of the industry and the supply that they should do to balance and optimize for their profit. Same for marketing. They know that they have to invest some amount in marketing to get some amount of revenue and sales. For manufacturing, they do a lot of prediction. How much time is the product going to take? Is there going to be any delay? What are the delivery schedules? Are there any cash balances? Suppose they want to buy a new product, but they don't have cash, right? So they have to manage their cash accordingly, right? In finance domain, let's say price of a stock, price of a property, price of futures, options, all of those, commodities, etc. Healthcare, obviously, there is diabetes prediction, health score from vitals. You must now know that there are watches that can actually predict if you are going to have a heart attack soon, right? Depending on your heartbeat and different other metrics, they can actually predict if you are prone to a heart cancer or a terminal disease very soon, depending on your vitals. Automobile, they use the different weights, engine capacities, engine dimensions to predict the speed, efficiency, resource utilization of the car, right? And there are many such use cases. Okay. Coming to types of regression. I see a question. Is it only through visualization we can determine whether it is linear or non-linear? So Dhaval, yes, I agree. You can test in other ways also, but visually it's the best because a lot of measures can have drawbacks. But once you look at visually and you know it is looking like a straight line, you can't go wrong. Okay. But let's say you fit a linear regression model and you got the accuracy of 90%. And then you fit a non-linear regression model and your accuracy decreases. That tells you that it's a linear regression requirement, right? But if you fit a linear regression model, you get an accuracy of 80%. And then you fit a non-linear regression model and you get an accuracy of 95%. That tells you that the relationship was not linear. But all of this are after you've trained the model. Before training the model, before doing anything algorithmic, can you just look at the data or observe the data, analyze it to see if the relationship is linear or non-linear? Obviously, for small data, you can visualize the data, look at it and do it. For large data, you will have to do a lot of complicated visualization. Okay. Neha, univariate basically means there is only one independent variable, only one controlling factor. Okay, multivariate means there are multiple controlling factors for the output. Are there any other questions? Okay. There are multiple models for regression. First of all, regression is divided into two types: simple or univariate, multiple or multivariate regression. If you have only one feature, then it's a simple simple regression or univariate regression. If it has multiple features, then it's a multiple regression model or a multivariate regression. Both are the same thing, different ways to say the same thing. Okay. Another thing is the regression can be either a linear model, straight line based, or it can be a non-linear model, curve, quadratic, biquadratic, cubic equation, any curve, right? It shouldn't be a straight line. That straight line would mean a linear model. And multivariate also has linear and non-linear. Linear regression is obviously a linear regression model. Polynomial regression is a polynomial regression model. Now, what do you mean by polynomial? When you look at this equation, y is equal to ax plus b. Okay, again, a is my slope, x is my independent variable, y is my dependent variable. Okay. Yeah. So A is basically strength and character, X is independent variable, B is the constant, and Y is the dependent variable. Now, if you observe closely, Y is equal to AX plus B is a linear relation Y because the power of X is 1. A into X to the power 1, right? The maximum power of X is 1. That means direct relationship. But if my equation was something like this, ax square plus b, if this was my equation, then this would be a polynomial equation. Okay, obviously this is called quadratic. If it would have been x to the power 3, then it would have been a cubic equation. If it would have been x to the power 4, then it would have been a biquadratic equation, right? And the family of these relations are called polynomial. Okay, power greater than 1 becomes a polynomial equation. Okay, so you can have polynomial regression models also. Then there are vector-based separators, vector-based regression models. Ridge regression model is also a combination of polynomial and linear regression model. There is lasso regression, there is logistic regression. There are tree-based models also, decision tree and random forest. So what are tree-based models? Look at this image. We'll find an appropriate image for all of you. Yeah. So it will have a tree-like structure like this, right? This x1 is the independent variable. If x1 is less than 31.5, it goes to the left. If x1 is greater than 31.5, it goes to the right. And then there are several filters that it does to ultimately predict the numerical continuous value, right? And these are called tree-based models. Their structure is like a tree. So there is random forest, decision tree-based models as well. Okay. Now, simple linear regression is one input variable, one output variable, and this is your curve. Okay, you have to always understand that the relationship should be linear or not. So look at this. In this particular case, the relationship is linear. Okay, in this particular case, the relationship is not linear. Why? Because if I want, I can fit a much better curve on this chart. Yes or no? If I want, I can fit a much better curve to this chart, right? Just look at this chart. I can have a curve that fits these points like this, right? So this is a much better fit. If I'm trying to fit a linear model to a non-linear data set, then it is stupidity. Okay. Now look at this. This would have been a better curve. Okay. But why did the blue line go here? Because there is an outlier. So before doing linear regression, we should also remove outliers, because outliers can impact a linear regression model. The line was supposed to be like this, but the line got rotated here. Okay, because of this outlier. Now, this is also a special case. In this particular case, y and x have no relationship. Understand carefully. No matter how I change x, you see, for the same value of x, for the value of x to be 8, I have so many values of y, different values of y. That means x does not directly change y. There is some other factor that I don't know about. So this is also wrong, because this is not a relationship. This value is an outlier, and because of this outlier, a linear model has been created. But it is actually not a linear model. It is a straight line. The value of x remains constant and the value of y keeps on changing. So x does not impact y. Okay. These are the kinds of cases that we should be careful about. Okay. Now, let's talk about how does which columns. Azhar, I'm sorry, when you use median and mode, which columns? I did not. Oh, that was just an example, Azhar. A lot of different models, decision tree, random forest, they use different measures. Okay. So mean and median, it depends. So a tree-based model, I hope that's what you're talking about. A tree-based model is largely constructed on the basis of separation. Okay. So let's say if I split on the basis of a threshold, does that create a major difference in my output or not? Right? Let's say, just giving you an example. If you have a classroom where one side of the class is where all the boys sit, and one side of the class is where all the girls girls sit, right? If you split from the middle of the class, right, then based on that split, one side is completely boys and the other side is completely girls. But if you split like this, okay, I mean not vertically, but if you split horizontally, then on one side there will be girls and boys, on the other side there will be girls and boys. So a decision tree will try to split the first way, where the resultant segregation causes difference in the output. Okay, it will not split horizontally, it will split vertically, so that after the split there is less, I would say, diversity across the output. Okay, I hope that makes sense. Azhar, let me know if that's clear or not. If you have a follow-up question, also let me know. Okay. Okay, so I think these two curves are not working. Let me give you an example. Okay, so look at this curve. Look at this video, short video. This actually explains us how a linear regression line gets fit. Okay, it starts with iteration 0, where it is just a random line. Okay, it has no understanding, no learning. It's a random line. After multiple iterations, it tries to and achieves the fit. Okay, it gets the fit that it is supposed to get for all the data points. We will learn how this gets the fit. Look at this video also. If you observe closely, it is calculating the distance of the line with every individual point. It is calculating the distance between the line and the blue points on the screen. And depending on that distance, it is rotating the line to reduce the distance between the line and the points. Okay, I'll repeat myself again. It is evaluating the distance between the blue points on the screen and the green line, and it is trying to move the line in such a way that the distance between the point and the line reduces. The overall average distance reduces, because the lesser the average distance, that signifies that the line is able to understand the blue points and their relationship. Okay, let's look at this also, another example. Okay, the initial iteration is such that the red line is random. Okay, then slowly and steadily with every iteration, it tries to reduce the error, reduce the distance between the blue point and the line. And by reducing it and moving it in a particular direction, it achieves the best fit. Okay, now let's look at it mathematically. Okay, if you observe closely, let's say there are these 4 points. Okay, this is one point, this is another point, this is another point, and this is another point. These points are the true values, which is reality. Okay, these are true. This line is an estimate or a model that tries to estimate the relationship between x on the x-axis and y on the y-axis. This line gives us an estimate of the relationship. This is the true value. Now for this particular blue line, what is the error? The error is the distance between the point and the line. Okay, the distance between this point and the line, the distance between this point and the line, the distance between this point and the line, right? The sum of all these distances is what is important. But there is a problem. What is the problem? The distance between this line and this line is positive because this line lies above the line. The distance between this point and the line is again positive because the point lies above the line. But if I try to find out the distance between this point and the line, the distance will be negative because the point lies below the line. Same for this case, the distance will be negative because the point lies below the line. Okay, how do I solve this problem? I am going to square the distance. I am going to square the distance. After squaring, everything will be positive, right? Because earlier when it was negative, the positive distance and the negative distance will calculate and it will remove it. They will balance out each other, right? They'll cut off the total error. What is the error? This is the error plus this is the error. But if I add them, the minus will cancel out the positive and it will only show a small error. But I want to treat both of them as equal amount of errors. So I will square them so that the sign is neglected. And then I will find out the average squared distance between the point and the line, which in technical terms is called sum of squared residuals. Okay, in technical terms, this is called sum of squares. That is why we want to minimize and find the least squares, right? We want to find a line such that the output, the final fit line, has the least squared distance between the original points and the fitted line. Okay. For that, we do some amount of mathematics. How do we do? We'll first find out the equation of sum of squares. Okay. Sum of squares is the equation we will find. If we plot the sum of squares, it will look like this. Okay. Let me give you an example. Okay. Suppose this is my true line. This is my actual line. Let's say I start from here. I start from this random line. In the first case, my error will be very high. Right? My error will be very high from this line. Let's say I am at this point where my error is very high. Upon basis of the error, I will rotate this line. Let's say my new line will be something like this. Okay. Again, my error will reduce. Okay, because now it is closer to the points. Let's say again, after I rotate the line, this becomes my new line. Okay, this becomes my new line. The error is further reduced. Now there will come a point. There will come a point where I will finally have my line, which is the best fit line. This will be my best fit. Okay, where my error will be minimum. Okay, minimum error line. Let's say I further rotate the line. I make the line like this. My error will increase. Or I make the line like this. My error will further increase. So this particular point where I have the minimum error, what is a characteristic property? The minimum error will have a line 0. Like this, we'll have a straight line. In mathematical terms, this is called derivative of the sum of squared residual functions will be 0 at the point of minimum. Sum of squared residuals is a function. What is the function? I will do y minus the value of y based on the line. Then I will square it. Then I will do it for all of my individual points. For each of my points, I will calculate the actual value minus the value of the line, and then I will square them. That is my function. If I do a derivative, which means if I differentiate that function and equate it to 0, where the derivative value is 0, where the slope is 0, that gives me the minimum point. And if you solve that equation, you will find out that the value of b, right? The value of b and m can be calculated. They have simple mathematical values. Okay. Now, obviously, we do not have to calculate them manually. We can simply implement it in Python, which we will see, right? So let's check it out. How do we implement in Python? So I'm going to open a Jupyter notebook, right? Linear regression implementation. Okay, I'm going to do implementation of linear regression. First of all, I want to get my data set. So from scikit-learn, I hope everyone here knows about scikit-learn. From scikit-learn.datasets, I will use the Boston dataset. Okay. The Boston dataset is a scientific dataset that has been given publicly available, made available for testing. So what is the Boston dataset? The Boston dataset has data, which is this. I am going to convert this into a pandas data frame so you guys can view it easily. I mean, everyone here is acquainted mostly with pandas. So you can see this is the data. I'm also going to get the feature names from the Boston data, which will give me the input. So these are my input values. It is going to be a multivariate regression model. Okay. This becomes my data frame. Okay. The Boston dataset also has the target, which is the value I want to predict, which is the price of a house. Okay. So this becomes my Y value. Okay. Now, because I'm doing machine learning or implementing linear regression model, I will have to train test split my data. Scikit-learn dot pre-processing, I think. Not pre-processing. Model selection. Let's say. Yes. So train test split df and y. My training size will be 0.7, right? X train, X test, Y train. I hope everyone has learned this in InsideAIML classes. So I have divided my data into training data and testing data. Now I will import the linear regression model from sklearn.linear model import linear regression. Okay. LR is equal to linear regression. I'm initializing my model. LR.fit. I'm fitting my model to my training data. These are the basics of machine learning. If anyone does not know, I'd highly recommend going through the courses. I have fit my linear regression model. And now I can predict using my linear regression model on the test data. And you can see my model was created. What was my actual test data value, which was Y test? So this was my actual value. So look at this. My actual test, my prediction was 3.64 into 10 to the power 1, which is 36.40. My actual value was 35.2, right? My prediction was 27.70. The actual value was 23.9. So if I want to summarize, I can use the scikit-learn metrics, import mean squared error, so that I can find out the mean squared error. So mean squared error. I can pass the predicted value, which I'm going to put in a variable Y prediction. I can pass the predicted value and I can pass the actual test value. And I will get that my mean squared error is 22.97. If I root it, basically, if I do to the power 0.5, which is square root of this, then I get 4.79. So 4.79 units error in building this linear regression model, right? Now, if you want to look at the values, if you check this coefficient and you have your Boston feature names. So you can see CRIM, the variable, the input, has a minus 0.118 because it's a 10 to the power minus 1. So one decimal will shift. So it has a negative impact on the price of a house. ZN has a positive impact because the sign is positive. Similarly, Indus has a positive impact. CHAS, which is this variable, has a positive impact, right? NOx has a negative impact. All the positive values have a positive impact. And how much impact do they have? That is the number telling us, right? Which is the strength of the impact, right? The linear regression model also has the intercept, which is the constant value. So 33. 33 is the constant sales value. Now these things actually impact the value. Otherwise, by default, this is the value. So what will the equation look like? Sales is equal to CRIM into the coefficient plus ZN into ZN ka coefficient plus dot 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 for all the variables. Last may there will be a value which is constant, which is this. Okay. So this will be my multivariate linear regression line. Okay. So that was the implementation. Do connect with the InsideAIML team. If you need this notebook, they will be able to share this notebook with you via email. But this was a very simplistic, basic implementation of a regression model, linear regression model. There are multiple regression models. For example, you can do the same implementation on a decision tree. Okay, so this is the decision tree regressor model. Right, so I can do a DTR.fit. I can do the fitting on my train data. Right, and then I can do DTR.predict. I can do the prediction on my test data. Right, now I can save this value as a prediction. Then I can again calculate the mean squared error. If you check this now, my mean squared error has reduced from 4.79 to 4.24. Although it is not a very drastic improvement, so I'm still not sure linear, non-linear wala case, but I am still sure that the error has reduced because of decision tree. Okay, so that was an implementation. I hope you all had a lot of fun learning about the linear regression algorithm. It's a great algorithm to learn, start, develop your understanding about machine learning concepts, about relationships, about the fundamentals of ML, regression, classification, multivariate, univariate, linear model, non-linear model, training, testing, error metrics, etc., etc. Okay. So I had a lot of fun. If you have any questions, I will be looking at the YouTube chat. Otherwise, I will be seeing you all soon in the next webinar hosted by InsideAIML. Thank you, everyone. I am ready to take questions.